Welcome back, everybody. In this module, we're going to talk about non-normal data. What if your data doesn't fit a normal curve, a normal distribution? How do you still use it? How do you still make smart business decisions with this data? We're going to talk about how you can transform your data and make it still useful to you, and we're going to do that right now. Okay, non-normal data. What do we mean by this? Well, normally we like our data to fit a normal distribution. It looks like a nice bell curve. We have most of our data grouped in the middle by the mean, and then it slowly tapers off to those outliers on the outside. But sometimes data doesn't look like that. In fact, a lot of times data doesn't look like that. So we need a way to handle that type of data so we can still use it in our business. This is the normal distribution, and we understand that about 68% are within plus or minus 1 standard deviation. 95% of our data is within plus or minus 2 standard deviation. And the whole reason we like our data to be normal is because of that. We want to be able to quickly go back and forth between those percentages and standard deviation. And that way we can make predictions like, what's our process capability look like? Are we in control or not? But if our data is not normal, then it makes it a lot harder to make those decisions. So data sometimes just isn't normal. You can get a sawtooth, like a bouncing up and down in your data. Sometimes you have bimodal data where it's like there's two processes going on here overlapping each other. And I've actually seen this a lot in industry where, with orders, you'll see orders that go out on time, and that's kind of one distribution. And then you'll have a bunch of orders that are stuck waiting for parts or something, and those will be, 10, 20 days late. And those are a completely different distribution. So you get like this bimodal kind of a look to your data. And then we've got, skewed data. And this is really common as well. You'll see skewed data, particularly in shipping departments where a lot of the shipments go out really early. And then, they slowly taper off over time. And so you've just kind of got this skewed distribution off to the, hopefully on the early side for your shipping. We see it in the late side as well in some other examples. So skewed data is really, really common. I run into that probably more than any other type of distribution that you see on the screen here. Now, so how do we handle it, and why do we care? Well, because a lot of the tests that we use in statistics depend on that data being normal. So when you're doing a 2-sample t-test, it's assuming that your sample before and your sample after are both normally distributed. And if they're not, then it might give you a false positive and say, yeah, there's actually a difference between your two samples when actually there isn't, or vice versa, right? So a lot of the assumptions that are made in statistics are based on the assumption of normality. And we have actually different tests and different statistical tools we're going to use when our data is not normally distributed. So here's a list of the normal or parametric tests that are used when the data is normal, and the non-parametric tests that are used when the data is not normal. So when we're doing, for example, a t-test, that's assuming normality. If it's not normal data, we need to use a Mann-Whitney test or a Wilcox test. When we're doing analysis of variance or variation, we use a one-way ANOVA. If we have non-normal data, then we got to use a Kruskal-Wallis test. Spearman's is a lot more tolerant to non-parametric or non-normal data, so we want to make sure we're using that when we have data that doesn't look right. So just to recap, let me go through a few of the reasons why we actually care. Number one, non-parametric tests have fewer assumptions about the distribution of the data compared to parametric tests like the t-test. So again, parametric means it's assuming the data is normal. So that's a good thing, right? We can use the non-parametric tests on any data because they don't make as many assumptions. Number two here, non-parametric tests do not rely on the estimation of parameters such as the mean or the standard deviation. Again, most of our other tests are assuming that we've got this nice bell curve with a mean and a standard deviation. Number three, non-parametric tests use medians and ranks instead, so they're more robust. Number four, if the data is normal, of course it says are normal, but you guys know me, I'm going to flop back and forth between is normal and are normal because I don't care whether you call data a plural or a singular, it just doesn't matter. But if the data is normal and free of outliers, then a non-parametric test is going to be less powerful. So we would prefer to have normal data, and we would prefer to use the parametric or the normal tests. The other tests just aren't going to be as robust. We're going to need more samples to get a good answer or the p-value that we're looking for, a more robust answer in that p-value. Number five, non-parametric tests should be used when the data are non-normal and data cannot be readily transformed to normality. So we're going to talk about transformation here in just a second. Or if we have a small sample size, something less than 30 or some other amount, again, sample size, there's no general rule of thumb. You have to know how big of a sample you're trying to get to detect the signal and the noise. So if you don't remember that discussion, go back and rewatch the power and sample size module to understand how big your sample size needs to be for any given signal you're trying to detect. And finally, if the sample sizes are large, you can use the central limit theorem that says parametric tests are robust to non-normality. And we're going to talk about that here next. So what is the central limit theorem? The central limit theorem basically says if you have some non-normal data, you have some random data, if you randomly sample that data and take the averages of those samples, like let's say you have 1,000 data points and you randomly sample every 10 data points out of that, and you just keep sampling 10 data points out of that. If you take the average of all those samples, the averages of those samples will give you a normal distribution, or they will be normally distributed. So the central limit theorem says if you take enough random samples from a population, that these samples will eventually look like a normal data set. So why is that useful? Well, because we can use the central limit theorem and some other types of transformations to actually make our data appear to be normal when the original data set is not. So let's practice. Let's go through some exercises together of what we mean here. First of all, we have to learn how to test for normality. And then in SigmaXL, that's really easy. We can go to histogram and descriptive statistics, and we can test for normality. So I'm going to back out of my slides here and jump over into a spreadsheet here. And let's just create a new spreadsheet from scratch here. Okay, so I'm just going to hit Control N on my, and make sure you have SigmaXL open, right? Make sure you've got SigmaXL open up in the top here. To do that, you got to go to your desktop and actually click on the SigmaXL icon. If you open up Excel, just from the Excel icon, it won't automatically have the SigmaXL plugin activated. So once we have a SigmaXL open and a new sheet, we're going to click on Data Manipulation. And let's go create some random normal data. So go down to Random Data Normal, and let's just create 100 rows of normal data. Click OK. And now we've got some normal data. Let's analyze this data to see if it's really normal. So we're going to go to Graphical Tools, Histogram, and Descriptive Statistics. And we're going to just select our data here in the box. Got to select the whole column here. Let's try that again. There we go. Click Next and select our data, move it from the left box to the right box, and click OK. And that's going to spit out this nice little bell curve with the data underneath, and it's going to give us the average, the mean, the median, the mode, all that great stuff up here. But what we're looking for is our p-value. So right here at the bottom, p-value of 0.39. Now remember, the default assumption is that the null hypothesis is that the data is normal, right? Or the data are normal. So you're looking for a high p-value because you don't want to reject that hypothesis. If you get a low p-value, then you have to reject the hypothesis that the data is normal, and you have to assume that maybe it's not. So because we have a high p-value, in other words, it's not less than 5%, it's 39%, 0.39, brilliant, right? We've got data that we can assume is normal. If we reject that hypothesis, right, we're 39% chance we're wrong, which is not a good assumption. Now, but let's see what happens if we have actually, let's do one more thing here. So let's go to graphics and tools, go back to our data here. Graphics and tools. And let's click on normal probability plots. That's the one I'm looking for. Click Next. Again, move your data from left to right and click OK. This is what we call a normal probability plot. And what you see here is in the center, this line in the middle, this black line in the middle. If data were perfectly normal, it would all fit on this line. It would be like perfectly straight, right? There'd be no standard error there. And everything, of course, but to say that your data is normal, we want to see data points that fall within these orange lines, this top orange line and bottom orange line here. As long as our data is within those two orange lines, we're going to assume that our distribution is normally distributed. It's not going to be perfect, but it's close enough. And, that's what p-values are for, is to tell us what's the probability that we're wrong if we say it's normal. So if you look at the normal plot, all of our data is in between the orange lines. We're looking good. And that is again validated over here by our p-value of 39%. So we're in a good spot. Now, what I want you to do is we're going to actually go back and we're going to do a different exercise using non-normal data and see what that looks like. So right here, we're going to go to help sample data, non-normal cycle time 2, and select our data and see what that looks like. And you can see already it's going to be a little bit of a mess here. So let's go ahead and we can go to SigmaXL and we can click on help and then go to our sample data. If you get a warning that it's not a safe place to go, that's okay. Just click through on that. And then we're looking for our non-normal cycle time data here. What's it called? Non-normal cycle time 2. So we're going to open that up. So let's go here to sheet 1. We've got our cycle time in minutes. And let's see, how many data points do we have? We got like 30 data points. So great. So we're going to highlight that data and let's just see if it's normal. So click graphical tools, go back to our histogram and descriptive statistics. And let's just check that out. So we select our data, click next, move our data over from left to right, click OK. And yeah, you see our data, it does not fit a normal curve. It doesn't look good at all. P-value is 0.000. So no chance that this data is normal. So let's go back now. And now that we've analyzed that, we know that it's not normal. We could also do the normal probability plot. So go to graphical tools, normal probability plot, and we'll select next. Move our data over from left to right, click OK. And you can see here, we've got some nice alignment there. It's a pretty graph, but it is not between the orange lines. So nowhere near this black center line here. So it's not normally distributed. Pretty clear there, right? So what do we do with that? Well, we can transform this data. We can actually go in and make this data look normal by doing a transformation on it. And there are a lot of different transformations. So let's talk about that. Let's jump over here. So transforming your data before you analyze it will help it look normal. You can use the Box-Cox transformation, which I'll show you in a second. There's also a Johnson transformation. There's several other distributions that can be transformed. So you don't need to learn all of these different types of transformations and how and all the statistics behind them. At least I don't require you to learn that. You are welcome to go dive deep and, go into the statistics and never land and find out all you want about those. But we're not going to talk about that in black belt training. For black belt training, all you need to know is that there are different ways to transform your data and the software is going to do it for you. So great. Let's let the software choose for us and find the best way to transform our data. Let's start with that Box-Cox transformation. We're going to jump back over here into our Excel sheet and we're going to do a Box-Cox transformation. And there's two ways to get to that from SigmaXL. The first is you can go into your process capability menu here and do non-normal and then do capability combination report. And that's going to actually do a process capability analysis and do the transformation for you at the same time. But before we do that, I want to show you how to do just the Box-Cox transformation without any help from the CPK menu here. So let's jump back to our cycle time and we're going to select that data and go to data manipulation. And you'll notice there's a Box-Cox transformation button right there. So if we select our data, click next, move our data from left to right, and then you'll notice a couple of options down here at the bottom. Number one, do not store transform data if the lambda equals 1 falls within 95%. What that means is that if the transformation doesn't increase our probability of our data being normal, then we don't want to use it. So I have that selected. And then the next one, do not store the new transform data if it's not normal. In other words, the transformation didn't work on this data, which sometimes it doesn't, right? Sometimes your data can't be transformed using at least this transformation. It just doesn't work. So if that's the case, we don't want to store it. And we'll keep it as a rounded lambda. Lambda is the variable that it uses to transform the data. And then we're going to click OK. And voila, we get a cool graph here that is our Box-Cox transformation and our lambda score here. And then on the right, you can see what we really care about, which is our p-value for the transformed data. So you'll notice that p-value is what we want, greater than 5%. So 40% p-value. If we said our data is not normal, there'd be a 40% chance that we're wrong. So that's fantastic. And again, the optimal lambda that's looking for is 0.06, so a lower lambda right here. And, the final lambda that we got here of 0 is within this range. So if you're interested in that, it's basically saying how well did the transformation work using the assumptions we made for lambda, which is our transformation coefficient. And then over here on the right, we've got our original cycle time data and then our transform cycle time data. Now, key thing to note here, your units change when you transform your data. So if you're measuring, units per hour or feet traveled per minute or something like that, those units no longer apply once you've transformed your data. Your new data set does not have those same units. So you can't use the same, if you're doing a process capability test, for example, you can't use the same units. So going back to this, we see that our cycle time, was transformed into a bunch of numbers between, it looks like, 3 to 8, right? Okay, great. Is that data normal? Well, let's check it out. So we're going to select it. We can go SigmaXL, graphical tools, histogram, descriptive statistics, select that data, move it from left to right, and voila, there is our transform data. It's got a mean of 5.9, standard deviation of 1, a range of 4.89, and a p-value of 40%, which we already saw back here with our Anderson-Darling p-value on the transform data. So that's good. Let's see what it looks like on the normal probability plot. Graphical tools, normal probability plot. We're going to hit next, move our data over from left to right, and OK. And this gives us our new probability plot for our transform data. You can see it's very nice and normal in between the orange lines. Fantastic. So what is the practical application of transforming your non-normal data back into normal data? Well, primarily you're looking for application where your process was maybe out of control, but when transformed, it actually is a normal process that's in control. Or perhaps you're looking for what's my process capability? Is my process able to meet the customer specification? Well, when it's normal, you can't tell because you can't look at, the normal 65%, 95% that's within spec, because your data is not normally distributed. By transforming it, you can figure out what percentage of the time you actually can hit a goal based on the type of data that you're dealing with. So let's look at the data set that we have now, and let's check it out with a normal or an analysis using normal, an assumption that's normal, and then a second analysis where we actually transform the data. So we're going to dive right in here to our cycle time, and let's go to our process capability. And let's just analyze this as if it were normal. So histograms and process capability. We hit next. We move our data from left to right. And let's put in an upper spec of 1,000 and click OK. So what do we get here? A mean of 703, standard deviation of 1,181. And our expected overall performance, the number we care about most right here, is the total percent out of spec. Right. So right now that total percent out of spec is about 40%. Right. Okay. Is that real? Right. Well, our data's not normal. We already know that. So if our data is not normal, what do we do? Let's go back to SigmaXL. Well, first we'll go back to our data here. Let's go back to SigmaXL. And this time let's look at process capability, assuming non-normal data. And when we do that, we can go to the capability combination report for individuals, non-normal. Again, we're going to select our data, move our data from left to right, and then put in our spec again of 1,000. Now there's two more options here. On the left-hand side, it will automatically generate control charts for you if you want them. And so, yes, I do, of course. I want to see control charts to see if my process is in control or out of control. So I'm going to select that. I'm going to select test for special causes. Anytime you do a control chart, you definitely want to test for special causes. And then down below here, it has the option to default to Box-Cox, Johnson transformation, automatically specify the best fit, or pick a specific distribution, which if you already knew your distribution looked, skewed, for example, like a logistic 2-parameter, 3-parameter, smallest extreme value. If you knew that, great, you could select that, but why would you? Just let the software pick. So let's look at a box Cox first. Rounded lambdas, a good assumption there, and click OK. Wait for it to think a little bit, and there we go. So there's our spec limit. There's our normal distribution plot. And if we look down below, the Anderson-Darling normality test gave us a p-value of 0, which means we'd reject the hypothesis. Our original data is not normal. However, if we look at the transform data, we get 36%. I'll try to zoom in so you can see a little better. 0.36 p-value. So 36% chance we're wrong if we reject the hypothesis that the data is normal. So the transform data looks much, much better. And based on that transform data, our overall expected performance is about 17%. So 17% of the time we're going to be out of spec is what that means. Okay. So box Cox transformation seems to be pretty good. Down below that, it actually gives you a couple cool things. So it gives you a control chart. So here's your individual cycle time report. And if you look over to the right, no out of control data points for the individual measurements. This is, again, the transform data or for the moving range. So if we scroll down again, here's our moving range, no out of control points. Awesome. So with our transform data, we have a good process that's in control, and we have a better understanding of what percentage of the time we can actually hit the spec or not. Now, let's go back and see if there's a better distribution than the box Cox. So we'll go to SigmaXL, process capability, and this time we're going to go to non-normal capability combination report. Same process as before, except this time we're got to put our 1000 in again. Let's let the software do a best fit, okay, and see what it comes up with. So we click OK, wait for it, and voila. Now, for some reason, this messes up the charts for me, so I'm going to have to squish those back down. Give me 1 second here. Not sure why it doesn't like my screen on this one, but that's okay. Okay, so first thing to look at, there's our new transform distribution. And what distribution or method did it use to transform our data? Well, it used a log logistic 2p. Okay, so that's the transformation that it used. And down here below, again, we see that our original data is not normal, but with this transformation, the logistic transformation, we get 24%. But using a box Cox, we actually got a better number for our p-value. Let's look at our expected overall performance, 14.53%. Using the box Cox, if you remember, we got a 17%. So using this transformation, it means we're going to be out of spec. We'll have fewer parts or fewer times that we're out of spec. Why are they different? Well, when you're letting SigmaXL select the transformation for you, it's going to pick the best transformation based on the p-value. So it's going to run the numbers for multiple transformations to find out which one has the better p-value. That's really what it's looking for. So if you just go to the box Cox, you can use that. I would have confidence in that. You can let it select whichever transformation you want. Either one of those is going to work. The main point is that when you use the transformation, your percent out of spec is going to be more accurate to what's actually happening than if you're doing an analysis assuming your data was normal. So again, key things to remember here, let the software pick for you. That's always a good choice. You don't have to remember your different distribution types or be worried about if one was better than the other. You can see here again, box Cox, Johnson transformation, they're going to give you slightly different results. But which one fits your data better? You know, you could look at all of them and just analyze it yourself and make a decision. Another option here is that you can actually do distribution fitting. So if you click non-normal distribution fitting, select all transformations and distributions, you can then scroll down and check the p-value for each one to see which p-value is actually better and use the distribution with the highest p-value. And now you know how to take your non-normal data and actually transform it to make it useful for analysis. And it's applicable to almost any situation. So again, just let the software do the work for you and make sure before you do any data analysis that you're actually testing your data for normality. Plot it on a histogram with histogram and descriptive statistics. Now you know how to do a normal probability plot. So check it, make sure everything's within those orange lines. Check for your p-value. You want a p-value over 5%. And, you pick the transformation with the highest p-value once you transform it. And that's going to help you make much better decisions with all types of data and data that we find in business all the time.